When we work with right angle triangles, we have our side lengths labeled hypotenuse, opposite, and adjacent, which is great for right angle triangles, but we can't use them for other triangles that don't have a right angle because we don't have a hypotenuse. So the convention when we're naming them is we always want to use uppercase letters for the vertices of our triangles, and our sides are always labeled with the lowercase letter of the angle across from it, which I have mentioned previously. So I'm going to hop down to the bottom, or to the middle of the screen here, and I have an angle B, which I forgot to lock my screen. Let's try that again. Angle B here, which side across from angle B would be lowercase letter b. And here's angle C, the side across from it is lowercase c, and then we have angle A, the side across from it is lowercase letter a. All right, there's this thing called the sine law that is true. And I'm just going to give this to you to show you what it is or explain to you what it is. And then we're going to actually prove why it works or how it works. So our sine law looks like this. It can be written one of two ways. We can take the sine of an angle in a triangle, and if we divide it by the side length across from that, side length of the side across from that, that ratio or that division is equivalent to taking the sine of a different angle in the triangle and dividing it by the side across from it. And that is also equivalent to the sine of the third angle in the triangle divided by the side across from it. So let's talk about this and how we're going to prove it. What we're going to do with this triangle here, we don't have a right angle triangle, but we're going to use trig to help us come up with this sine law. So I have drawn the height in my triangle, and I'm going to label that h for the height. And I'm going to talk about how this works for a moment here. If I look at triangle, I'm going to make this contact point here, vertex D. If I look at triangle ABD, so in triangle ABD, so the one on the left, I could calculate the sine of angle B because I do have a right angle triangle. So the sine of angle B would equal the opposite, which is the height, over the hypotenuse, which is C. Now I could solve that for the height by multiplying both sides by C. So now my height is equal to C times the sine of angle B. Lovely. All right, now I'm going to look at the other right angle triangle. In triangle ADC, the one on the right, ADC, again, I'm going to look at the sine of angle C. The sine of angle C would equal h, the height of the triangle, the opposite to angle C, over the hypotenuse, which is B in that case. And again, I can solve for h. I can get h by itself by multiplying both sides by B. So times that by B undoes it, times this side by B. We're going to have h being equal to B times the sine of C. But these two h values, the one we have here and the one we have here, they're the same h. They're equivalent. So if h is equal to c sine b and h is also equal to b sine c, it follows then that c times the sine of angle b has to be equal to b times the sine of angle c. All right, we're almost there. What we're going to do next is we're going to divide both sides by c. I'm going to divide by c. So that eliminates it here, leaving us with the sine of angle B equaling B over, times the sine of angle C over C. And now what I'm going to do is divide both sides by B. So I'm going to divide by B here, and I'm going to divide by B here. That's going to eliminate the B on this side. And then all of a sudden we have what we have upstairs, higher up on the document. The sine of angle B is over B is equivalent to the sine of angle C over C. So that's the one part of our sine law. Now we could do the same thing by constructing another height to a different side of that triangle and then comparing the heights again using our sine rule, and we're going to find that we get the third part added into that. So that's where the sine law comes in. I'm not making this stuff up. I couldn't make this stuff up. I'm not smart enough for that. All right, let's look at the example here. Solve for angle A. So the key with this, to be able to use our sine law, is you have to have one complete ratio filled in. You need an angle and a side across from it, and then you need one other piece of information to fill in. So to be able to use the sine law, we need one angle and a side across from it. So we need a complete ratio. Complete ratio. One angle and a side across from it. If you would rather use those words, you can. And then one other piece of information. So plus, I was going to make a plus sign, plus one other piece of information. One other piece of info. So like another angle or another side length. And that will allow us to be able to use this sine law. Now, one other thing I want to mention about sine law before I go and actually do this last example, or this example down at the bottom, this sine law can be written the other way. You could flip each piece over and do the side length compared to the sine of the angle, and that is also equivalent. Now, whatever I'm solving for is what I usually put on top. The unknown thing I put on top because it's easier to solve for. And you want to make things easy for yourself. Okay, so let's look at this example now at the bottom, which is now no longer at the bottom. I have been given angle B, and I know side B. Okay, so that is my complete ratio that I have. I want to solve for angle A, and I have side A here. So I want to solve for angle A. I'm going to put the sine of angle A on the top over its corresponding side, and that has to equal the sine of angle B over its corresponding side. And then we're going to fill in what we know. We don't know angle A, but we know side A is 20. We know angle B is 48. And that's over that's over 15 kilometers. To get the sine of angle A by itself, I'm going to multiply by 20, and that will eliminate the 20 that's dividing it. But to keep it equivalent, we do that to both sides. That will be punched into my calculator. It's going to give me a decimal amount somewhere between 0 and 1. So the sine of angle A is going to equal something here. Let me get my calculator. Now that gives me a 0.99. Now my diagram's not to scale, 0.9 approximately. And I'm keeping all those digits on my calculator. And to get angle A, I'm going to use that shift sign, or the second function sign, the inverse function of sine inverse of 0.9909. That's going to give me A is approximately equal to 82 degrees. Now, angle A here doesn't look like it's 82 degrees, but we'll go with that. It's 82 degrees. In grade 11, you learn something called the ambiguous case of the sine law, where we can do some other things with that, but deal with this for now. Solve for side F. So for part B, we want to solve for a side length. So I'm actually going to put the side length on the top. I'm going to make it F over the sine of angle F. So I can just switch my letters to match what I have. So I want F over the sine of angle F. Ooh, I don't have any of that information. But I do have a side length here and an angle here. So I could use D over sine of D. So I do have a complete ratio, and I do have one other piece of information. But before I can actually go into the sine law, I'm going to solve for angle F using the fact that my angles in a triangle have to add up to be 180 degrees. So let's subtract these amounts here and get our value. So I got my angle F being 75 degrees. I can now put those values into the sine law. And again, I always include the degree symbol because if it doesn't exist there, it's assumed to be radian measure. So it's good practice to put that degree symbol in there. Of course, I know that we're working with radian measure, but not everybody would. All right, to get angle F by itself, I'm going to multiply both sides by the sine of 75 degrees, times this by the sine of 75 degrees. Oh, I was able to move that over, good. All right, and so then side F, I'm going to put that in the calculator, 19.5 divided by the sine of 35 times by the sine of 75. And again, make sure you're in degree mode. I get about 32.8. 32.8 meters, going to one decimal place. All right, so your sine law can be used when you know an angle, a side across from it, and one other piece of information. Sometimes you have to do a little extra, like we did here, where we have to solve for an extra angle, but otherwise it will work. So just make sure that you are able to make the two little ovals like I have in the diagrams above to be able to answer the questions using the sine law. All right, let's take a look at some more examples here. An architect designed a new building that's 12 meters wide. So I'm going to mark that on the diagram. The 12 meters would be the width along here, which would be equivalent to the width along here as well. The roof consists of rafters of two different lengths. So the rafters are the parts that make up the peak of the roof, and they meet at an angle of 80 degrees here. The long rafters make a 135-degree angle with the exterior wall. So this looks, the longer one would be the one here, and the angle they're talking about here is 135 degrees, that whole angle. How long should the carpenter cut the shorter rafter? So this is my shorter rafter. I'll mark that with an X. Now, I know that walls should be perpendicular to the horizontal. So if that's 90 off of the 135 would be a 45-degree angle here. All right, so I need to find the X, and I know the angle across from it, and we have a side and an angle across from it. So it looks like a sine law is in order here. So I'm going to put my side length on the top since that's what I'm trying to solve for. Sine of 45 degrees, and that's equivalent to the side length over the sine of 80 degrees. Multiply both sides by the sine of 45 degrees and you can solve for X. And when I put that in my calculator, I got an 8.6 meters roughly there. All right, so to one decimal place. The short rafter should be 8.6 meters long. Now we still need to find the long rafter, which if I use the angles add to 180, I could figure out what the missing angle is and then be able to solve for my other value, which I'll make a Y. So when all said and done, I got 9.981465. If I round to one decimal place, the 8 technically tells the 9 to go up by 1, which then that rounds it to 10 decimal 0. To indicate that I've rounded to one decimal place, you want to keep that decimal 0 there. All right, last example here. Angle measurements were taken from 2 points directly opposite sides of the tree as shown. How high is the tree? So we want to find this height in here, which would be a 90-degree angle to the ground. That gives us a couple right angle triangles. But if I look at my right angle triangles, I have angles in them, but I don't have any specific side lengths. And because these two angles are not equivalent, the 30 is not equivalent to 40, I can't just divide 85 in half. It's not going to come down exactly in the middle. So we're going to use sine law here to solve for one of these unknown side lengths. You could either solve for X here or Y here. The side you know is 85, you're going to need to solve for the angle across from that so that you will have a complete ratio to work with. So give that a try and see how you end up. Different ways to solve this. Yours might not match mine, but in the end we should get the exact same height of the tree. So I solved for the angle on top and got 110 degrees. If you're solving for side X here, then these are the processes that I would go through to solve. I got X being 58.1, and then I used the right angle triangle on the left of the diagram to solve for the height of the tree with my SOHCAHTOA, because sine, we have opposite that we're trying to solve for, and we have the hypotenuse now that we solve for X. We could also have figured that out using our Y value instead. So again, this is what I'm doing over here, and then I'm using the right angle triangle on the right to be able to calculate the height. But in either case, the height of the tree is about 29.1 meters. So the tree is about 29.1 meters tall.